Okay, it's about the time. I'm gonna go ahead and get this started. Okay, even though that no one has yet showed up, doesn't matter. Okay, so we're gonna record this one. We're gonna I'm gonna put this up in that our the website. Okay, so you can easily access that one. So let's go ahead and see what. Let's continue the same discussion that we had yesterday. Let's look at that our homework. Okay. Let's look at our homework back again. You can remember that yesterday that we did all the way up to question number 4 actually. So if I gonna that refresh our that memory, and plus that I wanna bring to that over here that another point that we can remember that we were talking about how to get the probability. This one, this part. See, when that how likely we would randomly draw a sample of size this much. Okay, 157 with a mean higher than 61, mean higher than 61 millimeters. This one, the mean greater than 61, mean. Okay, mean greater than 61. So that one we got by getting the bootstrap of that sampling distributions of means, and for that one I check the tallies. Instead of doing this one, if you want, you can use the XP norm. Can you remember XP norm, probability of normal distribution, P norm? Okay, we can use that one too, because assuming that the Y bar would be normally distributed according to the central limit theorem. Okay, according to central limit theorem. So let's see. Here, see, P norm 61, mean is 61.1, standard deviation is 8.73. 8.73 divided by the square root, see, 157. Can you remember? Yes. So we're going to assume that this would be fitting into this distribution. See, this one. See, from this distribution, see, I'm going to see this one. See, is 8.73 divided by a square root 157 is the standard deviation. Mean is 60.1 and cutoff value is 61. Okay, let's run this one and see. Can we get this one using the same thing? See, 61 mean. I'm gonna run that one. See, 0.90. So they're gonna give the area to the left of that one, not to the right. We need the area to the right actually. See, probability greater than, but the program will give you the area to the left. That means that if you run this one, I'm gonna write this one here, that part 2. So let's see, we have that one. How likely is this one? So the same thing, we can get it by, see, if I say probability, see, probability means P norm, see, probability of normal distribution. The cutoff value is the, this is a cutoff value, see, cutoff value. Let me write this one clearly. Cutoff value is 61. Then we put the mean which is 60.1. And the standard deviation is 8.73 3 divided by square root 157. Square root 157. Square root 157. We ran that one on our 61. This is cutoff value. See, 8.73. This one probability is 0.9070. 9070. Okay, 9070. No, 18.90. 0.90. 0.90. 87. 0.90. 80. 90, 80. But when we run like this, this is same as probability y bar less than or equals to 61. That's what it says. That means this part. See, it's very similar to that one. See, similar to that part. The program will give you the area to the left of that one, 0.9018, which is similar to 0.895, because when you're going to round that one to 0.90. Same way, this one also 0.90. See, 0.90. So that we can get it done, this one by tally. See, using tally or this way. Okay, tally or the other way. It's, this is same as the probability getting less than 61. It's very similar to this one. Less than or equals doesn't matter. Okay. Okay, let's get back to this one and see that what you have over here. Let's look at the homework 2. When we pick the first sample, see, we plot the histogram of the first sample with the vertical line going through the mean. Describe the shape of the distribution. What does the y represent? What does the mean represent? The notation, everything we talked about yesterday. Okay. Later on, we pick, we got that all the means were calculated, and then we plot the histogram for the age means histogram called the sampling distribution. Sampling distribution of the means. Sampling distribution of mean is nothing but the distribution of sample means, and we describe the shape. See, this one. So this is the one that we have over here. Can I remember yesterday? So we go to the first question. Can you remember? We pick a sample. I stick to this one, or anything, doesn't matter. See, I say I'm going to go to the data, my data. See, data, set WD, and then this one. See, and their dimension, their minimum, maximum, number of columns, number of rows. Call means that all the column means. See, you can get it. Row means you can get it. And we want to pick a first sample. So I go to the data. From the data, you can pick that one, or you can pick this way, this way, this way, anyway. But I pick this one. I call that one sample. See, I'm going to one sample. See, as a sample means that the data entry is in the first column. See, we got that one, and later on they're gonna ask us to what? See, got the histogram and then get all of that. We drew the histogram to the one sample, see, and do the vertical line which goes through the, see, it's mean, and we can even check the either this way, this way, this way, and then shape of the histogram is skewed to the right. Y-axis means the frequency of student, number of student each mean, and their mean. See, what's the mean of the first sample? 31.1, and its standard deviation. See, 6.1. See, we calculated that one. And later on, what would be the notation? Notation, you can say x1 bar and s subscript x1. See? S subscript x1. See? Okay, then second question was that instead of that one, they're gonna ask us to do what? See, I'm gonna go here. Okay, number 2. Question number 2. Number 2 actually. I prefer to put. I'm gonna get this one. The whole thing. Okay. Okay. I would like to start from here. Number 2. Number 2. Then these all I'm gonna say the note. You can say notes. Okay. Note. Then here again, keep going. I would say this one is, we talked about that one yesterday, various ways of getting this one. End of notes. End of notes. Okay, then let's go to question number 2. You can get this done either using apply. See, sample means you can get by using apply function or this way. Okay, see, apply data margin is 2 because you do column wise in your data set. Function is mean. See, you found that one. See, then I put that one into distribution, sampling distribution, SDOM. We call that data frame. And then I can find the head of this one or head of this one, same thing. And then draw the histogram for that guy. For the sample means, see, histogram. And then I found the mean of sample means center, which is 31.4, and standard deviation of that one is 1.25. See, 1.25 standard deviation. See? So see, then we got that one, part A, part B, then the distribution shape should be, because it's the sampling distribution now, sample mean y bar. This one is y bar. See, you pick the y bars, you get all the y bars. See, y bars. See? From the y bars, you built up what? You built up the sampling distribution. See, so that means that from the second, number 2, see, number 2, question number 2 in homework. See, you get the, see, you draw the histogram. See, y bars, all the y bars is a mean. So that one, see, that you saw the histogram. See, and going like this smooth flow scheme in the top on that one, you get the center. Center is nothing but, see, center is, see, mean, center is the mean. Okay, center is the mean. Center is the mean. That's the mean. Mean is denoted by mu of y bar, which is same as the mu, population mean. Population mean can be replaced by sample mean, which is y bar. Y bar can be replaced by observed y bar, which is, see, hi Benjamin, you didn't miss anything because that I was recording, and then I'm just going through that recap what we had been doing yesterday. Okay, you're not gonna miss anything. I'm just focusing on number 2 now, and then a little bit that refresh that one, and then we can keep going and then cover the whole thing. Okay, so I'm here. This one we did yesterday, but I want a little bit talk about that one a little bit. And on not only that one, then I want to bring to you before that, go to that one, something I mentioned here. Can you remember that this probability we calculate? This probability. This probability I'm talking about relating to this one. See, I added another one. See, the area to the left of that one, by using the tally, we can calculate. Not only that one, we can use the p-norm as well too. See, if you use the p-norm, cutoff value 61 and mean would be 60.1, standard deviation 8.73, see, divided by 157, that would give you area to the left. That's what they're gonna give by our program. Then that means this one, but I really need the area to the right. Then by subtracting 1 from that one, you can easily get the area to the right. It's very approximately the same as what you got earlier, see, around like a 0.90. This one also 0.90. So this is the one that I was talking about. This one, p-norm 61. You use the p-norm as well in order to get that value. Okay. So that's something that I want to bring up over here. Plus that I'm still a little bit go through that one to show that graphically. See, mu ops, that when you run that one, if you put to the picture on this one, see, you get the 31.44, number 2, 31.44, 31.44, this one, see, this one is 31.44. And at the same time, the spread over here for the number 2, the spread would be sigma of y bar, which is spread means, I'm sorry, spread means the standard deviation. You can say standard deviation. Spread means standard deviation. Standard deviation means sigma of y bar, which is sigma over square root 10, which is s over square root 10, s obs over square root 10. S obs is nothing but 8.73 divided by 157. S obs, I'm sorry, is that 8.73? I want to make sure that S obs is S obs 4.14, no? See, 4.14. Sorry, this one related to different example because we were in homework. Let me go back to homework to see this one. This is the one. See. Then we get this one 4 point, not this one, because this is, we are on homework now. So that should be based on that one of the example. That's why yesterday we didn't get the answer. Okay. So it should be 4 point. That's the part I want to see. It's for the one sample. One sample. See, one of the first sample or second sample or third sample. I'm going to, for my convenience, I'm going to use the first sample standard deviation 4.14 as my observed value. 4.14. 4.14 is subs divided by square root 10. 4.14 divided by 100. No, we put this one. Then we get 0.414. But that's not what we're gonna get over here. I think we had that discussion. 1.25. This one. So instead of that one, 4.14 divided by because that standard deviation, they should think this is one of the standard deviation. This is the sample size of each and every one. 100. Square root of 100 is 10. So that should be 0.414. So that's why I was curious why it doesn't show that when it comes to the sample means of standard deviation of sample means standard deviation y bar minus this value and this value should be the same. They don't count same thing. Sample means standard deviation because this one we got from that sample means the second question. See here running the picking the see all the averages. I call the sample means and their histogram we prove that one. And then I found the mean of the all sample means. Then I found the standard deviation of all sample means. Standard deviation of the sample means is same as this one should be. Yes, there's some kind of a discrepancy over here. Yeah, we still see that one. But this value, see, standard deviation of the sigma of y bar, this y bar sigma. Y bar sigma is nothing but population divided by this one. Since we have so many of that the ops value, sometimes it might be the reason. See, I'm looking into that one. 4.14, 4.144, one of the samples standard deviation divided by sample size. One of the samples, see, this is one sample. One sample, 4.14. Mean is 31. This mean and this mean close, see? The means they same, see? Mean okay. See? That mean 31.1, this one 31.44, that's okay. But this is the issue. I don't see that. That's the problem is the sample size is 100. Has been repeated 1,000 times. That's okay to get this one. And that spread should be that one of the samples or the population. If you don't have a population, you go to the observed sample standard deviation divided by this one. But they give the 1.2. See, I have looking into this. 1.25, 250, 2504. See, 1.2504. Now, this both should be the same. But, okay, you can look at it. But then later on, okay. But anyhow, we're gonna get the value with the R, okay? The R value, we're gonna get 1 point, this one. This is the one that I'm expecting, 1.2504 is the one that I'm expecting here. Describe the shape, what does the y-axis represent, what this means sampling distribution means, what is the mean, what's the standard error. Standard error is nothing but the standard deviation of the sampling distribution of mean. That's the this one, this value, they're looking for this value, okay, this value in R, this value, okay. So number two, the histogram we draw, then a shape, we ask the shape, part C, part B shape would be the symmetric and therefore appears to be normal distribution. Y-axis represent the frequency of means and represent the mean from the 1,000 samples. Okay, then mean, how do you get the mean? Mean from the sample mean, mu sub x bar, we used to call. So this is the one, say, mu sub x bar here, because they are using x, okay, but I put the y, but that's okay. X bar, y bar, doesn't matter what x bar, okay, mu sub x bar, okay, y bar or x bar doesn't matter, okay, here, see, but since they have X bar, we're going to use the mu sub X bar. And then the sample mean, what is this one? Mean apply. Oh, then you can get the mean in this way too. That okay, standard deviation. See, sigma sub X bar, sigma sub X bar, sigma sub, I call the Y bar, but the X bar. Okay. In your case, doesn't matter which, whatever the letter that you have utilized, that you can say the bar for that one. So say we use a mu sub X bar and sigma sub X bar. And the third one, what we did was, instead of that one, we pick a like a sample, calculate the standard deviation for all these given data. All the given data, sample standard deviation. See? Now, see, apply and the function is standard deviation. See? When apply, we got this one, we got the standard deviation, see, various standard deviation. And then we go to the histogram of that guy, see? And then I found the mainly that I'm interested in these two, mean of that guy, 3.99, and the standard deviation of the sample standard deviation, see, 0.27, 0.27, 63, and then the mean we know, mean of that guy, the center, mean of the standard deviation. Instead of taking about the whole standard deviation, we can take into account the mean standard deviation of the standard deviation. That means in number 3, we draw a histogram of S, and this is the histogram. And then smooth curve scheme in that one. And then you have here center. Center would be mu of S. See? Mu of S. See? Mu of S. Mu of S. Mu of S can be replaced by, see, this one. It's already bigger, 3.99. See, 3.99. 3.99, you can see 3.99 or 6 or 7. 3.99 or 7. That's the C. So this would be very good estimate for this guy. The population standard deviation, mu of S. And the same way they are spread, sigma of S. See? Sigma of S. See? Sigma of S can be replaced by that sample standard deviation of that one, which is, we got here the estimate, okay, 0.2764. 0.2764. 0.2764. See? So the Y bar for this given data, the best standard, the best mean would be what? The best mean would be, this is the means. There are so many means. Look at so many means. On this axis, all the means, sample means. Out of that one, I got the center. Center is the best mean. See, you can say this is the best Y bar. See, best Y bar. See, this sample mean instead of C, which is sample mean 31.44. See, that's the best one. So what's the best standard deviation? I'm gonna get this one as a best standard deviation. Best standard deviation is nothing but this one. See, best sample standard deviation is 0.3 3.9907. I'm not going to go to the standard deviation of standard deviation. Instead of that, are so many standard deviations. See, out of this, all the standard deviation, I get the center one. It's reasonable. To represent all the standard deviation, I got this one. That's the best standard deviation for the whole thing. I need the best standard deviation. I need those two. I need those two. See, I need those two. See, in number 4, that's why, see, we were looking for what is the best estimate of the population mean, what's the best estimate of the standard deviation. See, so I really need that one. Best mean, I would say best mean is that value. See, best mean, and I need the best standard deviation. So I have all these two. See, which are see, 31.44, and the other one 3.9907. Now I'm gonna think in number 5. Number 5, what I'm gonna think? I'm gonna think now from this one, find the following. Then now we are trying to simulate sampling distribution of the mean with the 100. Now we have already utilized our data done. Now we're gonna simulate. This is a simulation. Is that a bootstrapping? No, simulation. Here simulating, see? It's not bootstrapping. I'm not resampling. I'm gonna use the sampling distribution of the mean of this one from the 10 student each. See, you have to do this one 100 samples, but this time you don't have 100 student, you have a 10 student. You're not going to do 1,000 times, you do the 100 times. See, but I'm going to simulate. See, look at simulation. We talk about simulate means you're going to assume that your population distribution is normally distributed with certain mean. What's the mean? The best mean and best standard deviation. That's why we figure out best standard deviation and mean from the data. That data been already utilized now. So with the aid of that one, we already utilize that one. See, now I'm gonna sim. See, I'm gonna go to the R norm. See, R norm, you can remember 100 student mean is best mean, standard deviation is this one. See, from that one I extract. I'm gonna generate data. See, I'm gonna generate data. See, see. This mean, what is this one? I'm gonna see. Oh, this is either way, this one or this one. This mean, let me see that where's the number 3, number 5. Sorry. That's number 5. Yeah. Yeah, this is kind of like a discussion we are built in up over here. Okay, up to here under the note, look at the kind of a see. If you want that, you can simulate data like this, and then see, you can take the tail, everything, and the mean, see, and the same way that you can use the GF histogram or just the, but they look the same. Why? What is the deal here? Let me see. SimSD or simulation. Oh, this is a standard deviation. This is for the both of them. Okay, you can generate if you want standard deviation or the means, but we are mainly focused on means. Okay. So what I'm gonna do, look at what we are doing over here. I'm gonna think about this something that we did earlier. I'm gonna connect to here. Can you remember we built up population distribution? Can you remember we built up sample distribution? Can you remember we built up sampling distribution? These three, we can get it done in several ways. That's what I'm going to show you over bootstrapping, simulation, and that kind of a setting over here. See, this is related to that example. This is related to this example that rolling a dice. See, rolling dice. Okay, I'm going to say rolling dice before I'm getting to this one. Rolling dice, that's example. Rolling dice example. See? rolling die experiment. That one. So that one. How do you build up the population distribution? I'm gonna think this is simulating, okay? Not the bootstrapping. Bootstrap part we saw that the other day that when we going through that one, resample 1 to 6 million, no 10,000, no 100,000 times. This one is simulated population distribution. How do you simulate? You go to the discrete uniform distribution. See, okay. Unif. Unif means uniform distribution. D stand for what? Discrete. R stand for random numbers. How many thousand? For that one, you are not supposed to give the mean and standard deviation. You are supposed to give the first point and the last point. See, first point and the last point. You can remember. I did that one using that, this one. I'm talking about this one. I built up this one. I built up this one using the resample. That means bootstrapping through the bootstrap. So the bootstrap, we built that up. See, that's a bootstrapping. In another way, this is a bootstrap. We did that one. Now, after that one, we learn about simulation too. Bootstrapping as well as simulation. See, in order to do the simulation, you have to know the distribution type. This distribution is uniform. This uniform distribution, if you know, from that one, you can extract the same way that we extract some data from the normal distribution. Same setup. See, look at. I'm going to extract from there. See, then I'm going to put that into a data frame. Outcome pop become a simulated population. Okay, that's what we call simpop. See, then see, I'm going to looking into the head of that one. See, these are the number already being generated. See, those numbers they generate. See, they generate from that distribution. See, discrete numbers. Then I'm trying to make some histogram. See, discrete histogram. See, those are the breaks. Breaks gonna go from 0 to 6 with the unit 1 increment of 1. See, going 0 to 6 with the increment of 1. Then look at the breaks. See, 0, 1, 2, 3, 4, 5, 6. Then I'm gonna draw the histogram with breaks. See, then they were connected to each other. Or you use the what? With the bins. If you use the GF histogram, you use the bins. Those are the bins. How to build up the bins for the, if you use the hist, you use the bins like this way. But if you use GF histogram, you don't need to build up that one. See, you already have that one being taken care by the bins. 6 bins. Same thing I did over here to get the breaks starting from 0 to 6. It has to say 0 to 6 breaks. Okay. And the same thing, bootstrapping, we have already done 1 to 600,000 or something. See, I put to the data and boot pop and head boot pop. See, I'm using the GF histogram. If you're using by any chance hist, make sure you put the breaks. And then I go to the sample distribution. See, look at that. I'm going to go to the RD unif, simulate sample distribution. Simulate sample distribution. First, I simulate the sample. Okay. Here, first I distribute, generate the population, then get the distribution. Histogram means distribution. I generate through the simulation process, RD unif. I'm going to get 24. See, data frame, breaks. See? If you want, I put the 1 to 6 for my convenience. See? Here breaks 0 to 6. Here 1 to 6. Doesn't matter. Let's see that if you put this on 0 to 6. Same thing. Break 6. Rather than that one, see, I call the break 6, or that you can say the breaks on 6. Then this one breaks here, okay. Go back to here. This one, and then come back, breaks. 0 to 6. Simulate sample. Simulated sample. SimSam. Breaks. List. See, from the 0. If you want, you can get from the 0 or 1 to 6. Doesn't matter. See, GF. And the bootstrapping. See, when you bootstrap this way, that part we have already done. See, like that. And the sampling. Sampling means you get the mean, go to the resample. This is simulated. I think this one should come first. Simulated one. Gonna cut and paste. This one, this one, two. Bootstrapping is the second one. See, now we get the simulated sampling distribution. Third distribution type. See, it's the code. See, uniform. No, it's not the uniform. Normal. See, uniform become normal. See, that's the interesting part. You see, you generate from here. See, and we put the mean and do this one and put to this one. The interesting part. See, they will become like this. Look at the variation, evolution of this or the variation of this distribution. In the beginning, uniform, and later on, like there's no shape. Sample has no shape. You saw that. Now it has like a clear shape. See, you get the clear shape. Or bootstrapping method. See, get idea how to do this. See? Before I go to the fifth question, that I wanna bring this up, because if you use the, and on the other hand, that RD unit can be utilized by, see, you have to install this one, okay? PURR, see, install this one, okay? Install package PURR, right? Library, this one, to get that distributions. Okay, I'm talking about the node. Yeah, node. Yeah, node here. This part I miss. You have to see. So that one. Then let's come to the fifth question. Now you can get this done using what? Simulated one. See, I call that one Q5 canvas. So if you want, you can see, because there are so many that simulations. So I call that one Q5 canvas or something like that. Whatever. See, I'm using the best mean and the standard deviation, and then do this one. See, these are my 100 data points. 100. Sample size is 10. Okay. Repetition 100. And histogram, can you draw the histogram? Yes. And can you find the mean? Can you find the standard deviation? See, they were asking about that question number 1 in number 7. Plot a histogram of the age mean with a vertical line at the mean. See, I did. Then find the mean of the, what is the mean of the sampling distribution of, see, what's the mean of the sampling distribution of the mean? See, 31.34. 31.34. 31.34, we use 44. 44 become 34. Doesn't matter. Very closely the same thing. And standard deviation. Look at the standard deviation. 1.31. 1.31. So you had, see, this is, see, look at standard error of the mean is standard deviation, sample distribution of the population standard deviation. Population standard deviation is this one, this SD. Okay, see, divided by square root of sample size. I go a little bit further over here. I would say base SD this SD divided by square root sample size is 10. No, look at that one. Let's say base SD was how much? SSD was 3.9907 divided by square root 10. 3.9907 divided by square root 10. 1.26. I got 1.26. 1.26. It is same as this one. 1.226, 1.3 to 2 decimal places. See, that's the same thing. See, that's the same thing. Kind of like roughly the same. See, this time it works. That's why I want to check on the other one. See, this time you got the sample because it's already generated. Because the issue is that where this data was coming from is not clear. That's why that here not like that. This one can be utilized. See easily that when they were coming from the normal distribution, it fits very well. See, so see we got roughly 1 point. I'm sorry, there's no negative. 1.26, 1.31. The same thing. Okay. See, no, this one is the Q5 dimension. See, look at here what we are doing over here. See. Mean vector, apply Q5. See, we're gonna say no. See, do this one R norm. I'm gonna generate this one, and if you want, you can get the what all means what all means do over rows. See, if you wanna do over and then find that sampling distribution, you can do like that. See. That's not related to this one, it's under the note. Okay. Then number 6, repeat the simulation Q5, but instead of 100 samples, get the 1000 samples. Same thing, that this time are 1000 samples. Okay, one mean of that guy, standard deviation of that guy, and histogram. See, part A, histogram. Part B, find the mean of that guy. Part C, again, see, standard error. See, due to standard error of mean, see, standard error of means, no, this one. Standard deviation of sampling distribution means standard error of means population standard deviation square root of sample size. Best SD divided by square root 10. Best SD is nothing but 3.9907 divided by SQRT divided by this time sample size still the same, no? Still the same. So that should be the same answer. Let me see whether we can get that. See, 1.27. This answer, see, 1.26. 1.26. It's gonna change. 26, 27. Change. That's the same thing. See, that's the same thing that I was doing. See, same thing. Again, from the R norm, if you get this one, you can do this one. Row wise, you don't have to worry about that one. Then the Q7, see. So what happened? What happened? See, what's the standard error of mean? What happened to the standard error of the mean compared to the simulation with the 100 sample for 10 students? 10 students. Look at what happened. The standard error is close to the same. It's not going to change. Even though you change the repetitions. That's the emphasis we are putting. You keep the same sample size for all the samples with the same size. But your repetition you change, it's not going to affect your standard deviation, standard error. See? Nothing. It says the same. RD. This happened because the increase in the number of samples didn't change the standard error. Increasing the number of samples. Increasing the number of samples, which is M, no? M. Can you remember M? We call M for that one. Number of samples means M. Didn't change the standard error. Then go to this one. We do a different kind of. Instead of this one, we keep this one 100. we're going to change the sample size and see what's going to happen. Okay. Mean, standard deviation you can get. You can draw the histogram now. See, they're going to ask about the mean. Mean pretty much the same. Standard deviation. Look at the standard deviation. If you get this way standard deviation 0.14. See, getting smaller now. Earlier, how much? 1.26. Now, see, getting smaller. See, larger the sample size, smaller the standard error. Same thing around. See? 1.3, 1412. This one around like a 1.3. See? This one, we don't need to this one again. Having more students per sample, that is 1000, as in Q7, gives a better estimate of the mean and a smaller standard error compared to the having more samples, 100 with the small number of students, 10 as in Q5. See? See? This can be compared. What happened to standard error of the mean compared to the simulated then with 1000 sample for 100 students in Q6? You did the 100,000 samples. See, having more student per sample, 1000 student per sample in Q7 giving a better estimate of the mean and a smaller standard error, better estimate, and the main thing that it pretty much it's at the center not going to change, but the standard error, the error that incurred getting smaller and smaller will give you best estimate. What that means, this is related to that that backward process. Backward process means if you have any estimate, how accurate that estimate would be. How accurate that estimate would be. By looking at what we're going to think about that, how accurate that one. That's the kind of a discussion we're going to build up in the next section. That means, see, you're looking into the confidence interval. How much confident that you're saying, then you pretty much you can say that. Can you remember standard error is playing that heavy role for your estimate? How likely you estimate? See, you can talk about that likelihood. See? You can say that 0.95 confident or 95% confident that our see data gonna be see estimate in the center. See, this is center. Center is okay. Center would be your mu y bar. I'm talking about y bar. Then mu y bar is same as mu. Mu is same as mu hat. Mu hat same as y bar. Y bar is same as y bar. Oops. That one we already calculated. In this one, this is nothing but 31.43. 43 or 44 doesn't matter. 31.44 again. See, that's the same thing that we utilize. 31.44. See. Okay. Now my question is how accurate this sample would be. How accurate? How accurate is estimate? How accurate this estimate? How do you check that one? You can check that you're gonna get this one. See, this is the likely region. This is unlikely region. That if you're gonna get into that one, it's unlikely that you're whatever that you're gonna utilize in order to get the best estimate. If you pick a mean from here, see, mean from here and here, they would not give you like a same that the estimate gonna go too far. See how far you can go like that. If you pick anything from this region, it's too far. That how see that bounds the cutoff values should be decided. How far that I can spread my that estimate, how far I can get the accuracy. Accuracy gonna go to not within like a just not that point. Accuracy can be given all the way up to here, accurate. See, those everything will be taken into account. But if you go beyond that one, That's unlikely. Unlikely means this will be distributed 0.25, see, 0.025, see, that means 2.5%, and the rest 0.025 gonna come to here, 2.5% will be here. See, see. So this one is nothing but we can remember, I call that an upper bound of, see, upper bound. This one is lower bound. See? So this whole thing is called the confidence interval. See? In another way, this is called the confidence region. Confidence region. Confidence region, CR. See? CR. Confidence region. This region. How much confident? 95% confident. These are called what? Rejection region. Rejection region. Both are rejection regions on either side. RR. See? Rejection regions. Who will be rejected? Your null hypothesis is connected to the testing of hypothesis. But anyhow, your center is not enough. That should be, that can be, how accurate can be decided by letting it to go to up to a certain threshold, above that one and below that one, and take into account all the values that in between those two will be best estimate. See? How accuracy would be this one. If you, there's accuracy would be this one. See? So that's why instead of that one, see, your point estimate, see, your point estimate for mean, population mean, is, see, the sample mean. Sample means observed sample mean. Sample mean. Observed sample mean. In our case, we have more than observed sample means. Okay. We have so many sample mean. Because of that one, I'm gonna get the means of sample mean. See, mean of sample mean. You don't have to do that one if you have only one sample. See, look at. See, see. Mean of sample means, which is 31.1, 31.44. 31.44. This is not what we accuracy. You cannot talk about. You cannot talk about how accurate this would be unless that you're going to go ahead and talk about the point is interval estimate. You have to talk about the interval estimate. To talk about this interval, that interval, you need the upper bound and lower bound. Upper bound and lower bound. How do you get the upper bound and lower bound? Upper bound is nothing but, see, I call this one, see, margin of error, maximum, see, error incurred. This is error. This is also error. From here to here, see, margin of error. See, margin of error. Error incurred by estimating the population mean, MOE. This one also MOE, above and below. Margin of error. Margin of error. So margin of error, to get that one, you need the spread. See, it will be definitely based on the spread. Spread of this guy. Spread of this one is nothing but, see, sigma of y bar. Sigma of y bar is nothing but sigma over square root 10, s over square root 10. See, s is 3.9907. In our case, number 7, the sample size is what? 1000, no? Sample size is 1000. Let me get back to this. Number 7. See, 1000. See, if you want, you can get this way. 0.14 or this way. 12. That's close by. I'm gonna go with the 1.14. See, 3.9907, 0.14, 0.1423, 0.1423, 0.1423. I need that one. I need that one to be I need now interval estimate. See, I'm gonna write here now interval estimate. Interval estimate of for population mean. Mean mu, comma, is this first one, this one. See, interval estimate. So what? I'm gonna say I need the confidence interval for mu. See, CI for the confidence interval. We can remember we had the discussion. Confidence interval for mu with what? How much confidence? 0.95 confidence. I'm gonna put that one to superscript. Okay. So this is nothing but y bar. Sorry, point estimate plus or minus margin of error. See? Plus or minus margin of error. Then the confidence interval of mu with the confidence, this one we're gonna call confidence coefficient. Confidence coefficient. This will be provided. It's nothing but 31.44 plus or minus. Plus will give you upper bound, minus will give you lower bound. Plus or minus, this one is CC. CC means cutoff value from the normal distribution times sigma over, sorry, I'm gonna say sigma of y bar. See, then 31.44 plus or minus C based on this value. This coefficient we're gonna call 1 minus alpha. This is alpha. 1 minus alpha. It's called 1 minus alpha, denoted by 1 minus alpha. This one, see, down the road. Cutoff value. Oh, cutoff value related to this one, 0.95 times sigma y bar. We already found it. This sigma y bar. See, sigma y bar is 1.1423. 0.1423. Then cutoff values are given to you. It's 1.95. 31. Those are standard value. 1.95 at cutoff value. See? And 0.1423. You can get that one. See? Right there. See? That will give you the range. See? Then this will split into, see? You can get the lower bound for mu, which is 31.44 minus 1.95 times 0.1423. You can get the upper bound of mu, which is 31.44 plus 1.95 times 0.1423. Later on, you can say confidence interval for mu with this point. Confidence would be, you're going to put the lower bound here, comma, upper bound of mu here. That will talk about the accuracy, okay? And get the value and put it here. We don't do anything by hand, but I'm showing you this one, that what's going on over here. See, accuracy. See, that means you saw that one. This is the guy is playing a heavy role. The smaller the value of this one, smaller the value of this one, smaller the value of the confidence region, confidence, and then eventually your mu come and then getting into what? Center. You're trying to get as narrow as you can that the confidence interval In order to do that one, you increase the sample size. See, you increase sample size. I would say, increase sample size and sample size. See, that will decrease what? Standard error of y bar, which is sigma y bar, which is sigma over square root 10, because it's see, it is inversely proportional. See, standard error going down. When standard error go down, what's going to happen? Confidence interval point, it goes down. And it goes down what? With a point estimate. So that means larger the sample, the smaller the standard error of y bar, which is standard deviation of y bar, and which will in turn that confidence interval getting narrower and narrower, rather than widening that one, and then your mu can come and settle down at the center, which is the sample mean. So sample mean and the population mean gap being, see, this you have a sample mean, sample, this is a sample mean, it's a population mean, look at the gap. This one called the error, that error. Error can be minimized, the gap between those two. If the mu can get in that, getting closer, this is nothing but mu hat and mu, that's the error. Narrow the confidence interval, the far better that of your point estimate would be. That's the kind of a discussion. This is related to the next that discussion we can have. As I say, having more students per sample, 1000, as in Q7 gives a better estimate of the mean and a smaller standard error compared to the having more samples with a smaller number of students. See, having no, having this number is this number. So number 7, we're gonna say that what happened to the standard data compared to the simulation 1000 samples for 10 students. 1000, no, more sample means 1000. 1000 samples. See, 1000 sample is a small number of students. 10 students, but 1000 samples. Here, having more students per sample, which is 1000. This is, I would say, n equals 1000. And this one, m equals 1000. This one, n equals 10. Okay. The larger sample size per sample related to the smaller standard error of the mean. Again, having a more student per sample, 1000 in Q7, what happened to the error of the mean compared to the simulation of 1000 sample for 10 students? See, now, oh no, this one, I'm sorry, this one 100 with 100. This one part B with the 100. What happened to the standard error of the mean compared to simulation with 100 sample for 10 students? Yeah. Having a more student per sample in 1000, see, n1000 as in Q7 gives a better estimate of the mean and smaller standard data compared to having samples, having not the more sample. This is not the more sample. So we can say having a more student per sample as in Q7 better estimate for the mean in a smaller standard compared to having few samples with a smaller number of students. See, they both few. Yeah, this one 10 and 1000. 10 instead of 10 students, but they keep the sample size what? sample size is 1000, simulation is 100. Simulation is 100. Not few, no, same. Yeah, same sample, same number of samples in 100 with a small number of students. So you keep the same, see, n only n gonna change. You keep the same sample, see, having a more student per sample. With, I would say, with m equals 100 samples. Both they would put the 100 samples, no? In Q7, 100 sample, Q 100 sample. Yeah, 100 sample, 100 samples. So having more, I would say that having more student per sample, which is n equal 1000 with 1000 sample, 100 samples in Q7. Is a better estimate of the mean and a smaller standard error compared to having the same number of samples, which is M7 with a small number of students. See? In 100 and this one. See? So this one will have more student will create a difference in that one. The larger the sample per sample relates to a smaller standard error of the mean. See? The larger the sample size per sample, I would say, the smaller the standard error. And the E again having a more student per sample, n equals 1000. This will be compared to the number 6. What happened to the standard error of the mean compared to simulation of 1000 sample for 10 students? 1000 samples. Yeah, number 7 we have 1000 sample, 1000 student per sample, which is this one with, I'm gonna say with 100 samples. With 100 samples. As in Q7. It's a better estimate of the mean and a smaller standard error compared to having the more samples, the smaller number of students. Again, 7-1 is compared to that one. This gives a better estimate of the mean and a smaller standard error compared to having more samples. M equals 1000. See, here m equals 100 with a smaller number of students. N equals 10. If you even though you change, see this one. See, we keep the same. See, look at m is 100. 1000 and smaller number of students will not give you like a better prediction. Better prediction coming through what? Increasing the sample size. See? Like that. Looking back at your histogram, except Q3, okay? The histogram that has the most spread in the is from Q1, where there was only one sample. See? The histogram that has the most spread is from Q1, where there was only one sample. Q1, look at them. One sample with 100 students, standard deviation 4.14. Question number 2, 1000 samples, see, 1000 sample with 100 student per sample, standard deviation 1.25. Q5, Q3, Q4, Q5, both Q4 is about the best estimate. Take out the Q5, Q3, and Q4 as well. Then Q5, 100 sample with the 10 students, see, this much. Q6, 1000 samples, see, 1 sample. I would say M equals 1. 100 student, M equals, see, 100. This one, M equals 1000. Sample with 100 student, M equals 100. The standard deviation. This one, M equals 100 with N equals 10. And again, M equals 1000. N equals this one, 7. We're going to go to M equals 100, N equals 1000. I increase the sample size. See, out of all these, see, standard deviation, if you check which one has the highest spread, more spread, how can you tell why this is so? I can tell that one from the histogram, the most spread, because I was comparing the standard deviation and standard error. This is due to the fact that the smaller the sample size, N, the larger the standard deviation or standard error, and vice versa. Due to the fact that the smaller the sample size, see, smaller the sample size, larger the standard deviation. We talk about that. We talk about the other way around. Larger the sample size, see, smaller this one, and the other way around. Smaller the sample size, larger the standard deviation, spread. Smaller the sample size, larger the spread. That's why it's like that. Okay, we know there's a connection from that one, both ways. And you can do that one both ways, okay, vice versa. See? Smaller the sample size, which is N equals 1. Larger this one, see, because it's in what? It's in the denominator, inversely proportional. Okay, so that's what we were talking about here. See, this is due to the fact that the smaller the sample size, the larger the standard deviation or standard error. See, standard error. See, Q9. Considering the estimate of the population mean from Q3, Q5, Q6, Q7, which estimate would you trust more? See, look at the M equals 1000 sample with N equals 100 student per sample, standard deviation this much. Then Q5, yes, you cannot make a decision only based on that, only based on the mean only. Okay, you have to go to both the mean and the spread. Okay, so M equals, look at 100 sample with 10 students. M equals 10. The next one, 1000 samples, same sample size. And now what? Smaller number of samples and larger sample size. We got pretty much same thing over there. The estimate that I trust the most is from Q7 because the standard deviation is the much smaller compared to the other results found in Q3, Q5, and Q6. You're gonna ask, which estimate would you trust most? One with the least spread would be trust because that, as I mentioned here, see, the accuracy can be, see, error can be, see, minimum. Then you have, see, standard error less. See, then a smaller standard error better. Smallest, better point estimate you get it. Confidence interval getting narrower and narrower. See? So because of that, see, one with the smallest one, which is in Q7. Results are usually more trusted when there's a less amount of standard deviation. See, that's why. Which estimate would you trust least? See, the estimate that I trust the least is from Q5 because the standard deviation, standard error is much larger compared to the other results from Q3, Q5, Q6, Q7. Q3, Q5, Q6, Q7. See? Q3, they are Q1, they have a drop Q1, okay, for that discussion. See? Results are very usually more trusted when there's a less amount of standard error. See, that means accuracy. More accurate your the estimate would be when there's a smaller standard error, standard deviation. Do you believe the sample mean and standard deviation you obtain in Q1 for one sample was a good estimate of the population mean and standard deviation? Why or why not? See? Sample mean and standard deviation that I obtain in Q1 for one sample is not a good estimate of the population mean and standard deviation. There needs to be, see, more sample sizes within the population since it is so large to have a better sample mean and standard deviation. When we test more variation of the samples, then we are able to see and understand the population better. Take for example, in question number 7, we simulated 100 sample with 1,000. See, 100 sample equals 100 samples with 1,000 n equals 1,000 students. That created a better estimate of the population mean and standard deviation was Q5. Estimate created a better estimate of the population mean and standard deviation versus Q5, where it was only 100 samples, see, versus Q5. See, this will be Q5 and they're going to compare this one. Okay, sorry, take example. Q7 has been compared with versus this one, Q5, where it was only 100 samples with 10 students. And Q6, where it was only 1,000 samples with 10 students. See, those two cases will be compared and contrasted with this one. See? See? So they ask that if you believe that if you pick like a one sample, would that be better, produce a better results? No, because we have to take into account the variation. That's what the bottom line. The bottom line is the variation. See? There needs to be more sample sizes, see? Within the population, since it is so large, to have a better sample mean and standard deviation. See? When we test more variation of the sample, then we are able to see and understand the population better. See? Like that. Okay. So you can add more into this one. Okay. So in the extra credit one, look at that R code to generate random sample of 100 coin flips from a coin where the probability of head is twice as likely as a tail. It should be that the probability of getting a head is same as that it should be is as likely as the tails, but this time it is twice as likely as a tail. Okay, it is being loaded. That means that the coins being loaded. To build up that discussion, I would like to go through this example. For this example, let's assume we are in a charge of quality for a factory. We make 150 widgets per day. Defective widgets must be reworked. We know that there's a 5% error rate. Let's estimate how many widgets we will need to fix each day this week. Number of observations, repetitions. You want to see for the size. Okay? Size. Number of times Y being observed. Y being observed. Let's say what that Y being observed. What do you mean by Y? Y is nothing but number of successes. Number of successes is nothing but number of defective, which is distributed according to binomial distribution. See, which has been given this setting. See, what that means? This means, okay, this means, see, this is a different discussion. Okay, this in extra credit one. See. See. So we think like each trial. See, each trial means we're going to call this one each trial. See, each widget may be defective, see, defective or non-defective. See, a different setting over here. Okay, it's completely that deviated from what we had a discussion, but we are trying to show you how to generate. See, defective or non-defective. I'm gonna call this one D, this one D bar to say non-defective. They say that there's a 5% error rate. Defective ones always what? The probability of, see, the probability of getting a defective one, I'm going to say PD. PD is given by simple P. Simple P is 0.05% always. See? And the other one I'm going to write PD bar. PD bar I'm going to denote by Q. Q is nothing but 1 minus P. 1 minus 0.05, which is 0.95 and 95%. In that case, see, this is a setup. Then we're going to see that how many size. See? N is sample size. N is sample size. How many widgets to be tested? How many widgets? Number of widgets. See? Here say number of trials per observation. See sample size. Number of observation, number of times Y being observed, number of trials per observation. How many times are you going to do this one? We're going to do this one according to this particular example. See, the example, let's assume we are in charge of quality factory. We make 150 widgets. 150 per day. How long are we going to do this one? For the whole week. See, must be rework. We know that there's a 5% error. Let's estimate how many widgets we will need to fix each day this week. See, this week. See, so this has to be, see, number of observation or repetitions. You want to see for the size. Number of times Y being. Y is what? That's the one that Y is nothing but number of successes. So here then now the sample size means number of widgets. Number of widgets to be tested, which is 150. See? 150. Okay. Then we're gonna pick something called Y. Y called the random variable. Random variable. It's a variable like a thumb length. Same thing. Normally we call this one random variable. In statistics we call random variable. Now I'm gonna say number of defective widgets. See? Number of defective widgets. How many you can have? See, this is a possible outcome. I'm gonna say possible outcomes. I would say possible outcome. None. 1, 2. See, keep going. 150. Which is see, all of them defective. And all of them. See, those are the possible outcome that can be. So every time that you pick, see, that check that one. See, all 150 if you check, first one defective or non-defective, defective, non-defective, like a flip a coin. Head, tail, head, tail, head, tail, head, tail, same, say head. See? For our convenience, we're going to call this one success. Success means we are interested in knowing that how many defective ones. This one is failure. See? That's a failure. So we can say Y number of defectives widgets they think distributed according to a binomial distribution. Binomial distribution with a sample size. We have to give this one. Sample size. Sample size is n. Sample size. The sample size of n equals 150 And probability of success. Probability of success means probability of defectives, which is P is 0.05. So Y is V, N equals 150 equals 0.25. It's like that. This means E is distributed. Distributed. See? Distributed. Distributed. Binomial distribution. No, not the normal distribution. It's a discrete distribution. It's a discrete distribution. Discrete distribution. Now, if you want to do this one, defective ones, in R, how do you get this one in R? See, for the whole week, see? In R, you generate. See? In R, you can get this one, defective ones, defectives. Defectives. See? You're going to go to R binom. R binom. See? Random numbers from the binomial distribution. R from the random. See? Binom from the binomial distribution. See? Binomial distribution. You're gonna first put the size. Size means like how many repetition. We're gonna do this on 7 times. See? And you generate 7. Then you put what? N. Then you put N. N is 150. Then you put P, 0.25. See? That's how you can generate. See? Effective one. See? See? That's what we are trying to do over here. They're gonna ask on average how many defective ones they're gonna find per day. But if you do this one 7 days per week, see? Sorry, if you do this one throughout the whole week, see? For this example, let's assume we are in charge of calculating blah blah. Number of observation, repetition, you want to see for the size, number of times Y being observed, 7. Then 7 times we're gonna do that one first Monday through Saturday, Monday through Sunday. See? Number of successes means Y, number of defectives, it's 150 probability of success getting trials one. See? Probability of getting a defective per trial. See? Number of trials per observation, sample size. Probability of success for each trial, this one. Binomial number of observations, see? Look at the number of observation size. R binom is a sequence, number of trials, probability of success. See? I put this one, see? Defective. Then I found the mean of that one, see? Mean of that one, see? 0.41, see? On average, then they're gonna ask, let's see, estimate how many widgets we will need to fix each day this week, each day. See, on average, we're gonna average it later on. See, you get their defective one. See, none, 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 2, 1, none, 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 2, 1. See, see, because there's a very low the probability of getting that one. So some people have already observed this a very low because of that one. There's no that many defective one. Let's say that for instance, if you change this one other way around, let's say the defective one is 0.95. Okay, let's say 0.95. Let's try that one. 95%. See, look at so many defective ones. At least 7. See, 7, 7, 7, 7. See? 6. See? 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 So see this one. See. Size 7, okay, and it should be 150. This one 0.05 means the lower one. That's why we don't have that one. Here, see what's this one. This one, come on. size 7. See what's going to happen. That's low means 0.34. Yeah, I mean, almost none. Almost none. 0, 1, 1, 1, 1, 2. Something. Let me see. Right. Sequence should be right. But the sequence say I put the number of observation size, number of tiles, probability of success. So out of 150 we have, see, if we make 150 we just per day each day. Mostly rework. We know that there's a 5% error rate. Let's estimate how many videos we will need to fix each day. See, out of 150. 150. Yeah, see, on average, see, 34 per day. See, on average, you don't have to do even a, it's not even a single one. Okay, let me see this one. Probability size. I'm going to switch this one and see. The same thing. So the same thing we're gonna do. See, you know, so I'm gonna come back to this one. So because see, this on average is none. That's true because the defective one is already 0.05 out of 100. Only like a see, like a 5%. Okay. So on average, see, flipping an unloaded fair coin, you get the same thing, size 1 in 100. See, they have 100 coins flip. Okay. Look at, see this one, coin flips 0, 1. Then if you're going to run this one for several days, you can find the average of that one. See, so coin flips, then they get the F table. You get the see F table for this one. See, 0, 50 and 150 because the fair coin. See, and mean of that one 0.5. Tails, see, 0.5. Mean will give you that percentage. See? Mean would be but nothing but is 50 divided by 100. 50 divided by 100. Okay. Let's say the unloaded one, the one that we're talking about. See, or you can do this way by giving the head and tail. See, I'm gonna say head and tail. You do this resampling, go to the coin flip. From this one, you're gonna flip 100. See, coin flip probability. See, tail head, tail head, tail head for this 100. See, first coin, tail head like that. Tally. See, 53 to 47. See, if you flip a coin, see, we don't know. See, unloaded coin, see how many we're gonna get it. Okay, that's another way to have a look at it. See, empirically flipping unloaded fair coin. See, unloaded fair coin, but this is empirically, this is classically, this is empirically, practically. If you flip coins, see, if you flip coin practically, there's no chance that you can get the whole thing. This discussion we talk about at a certain point. See, this is empirical, the unloaded, but still this theoretical one. Theoretical one, 50-50, you know that one. See, because this one says that one. This is practical. Now, our problem, we don't have a probability points. Sorry, the 0.5, we have 0.67 because the twice, say 2/3. Get in a see where the get in a head is twice as likely as a tail. 2/3. See, it's a unfair. It's loaded one. See, 57. See, coin flips. See, n equals 1. See, 57. 57. F table. See, coin flips. See, mean, tail. See. Now we're gonna do this one for what? See, if you do this one this way, see, 100. See, I do this one for size 100 and n equals 1. Instead of that one, I'm gonna do, see, n is 100, size is 1. Okay. See, 39 to 61, not to 50-50. See, and 61, around 61. 67 I put, but I get that empirically. See, get this one, see, this much. See, 0.39. That get the mean of these values, add all the values and divided by that will give you that average. Average is nothing but that each coin has like a chance of what? Getting that one, what? 100 coins. Each coin has a chance of 100. 100 times each number. Can you remember? Probability times numbers. Summation of this one. See? Probability times that one. See? So that's a kind of a that this question here. See, R binom. See? Can, see? This one, you don't have to do this way. So I think this is the right way of doing. N equals 100. See? Size is 1. You do only one time. You don't repeat it. See? At 100. See? If you do this one, see? If you do the other way around, see? N equals 1, then size is 100. Size 100. And N equals 1. See? Okay. See? 66. Only one coin. 66. See? 34. There's 34. If you do this way, you get the percentage. See? That's the difference. If you do this way, you get the number. See? Divided by 100, divided by 100. See? 100 minus heads. If you need the percentage, you can get the 72 divided by 100. See? 100. See? 100. See? This one divided by 100, 0.28 and 0.72. But you put 67, around that much. But when you do practically, when you generate that one, that number gonna change, okay? But you have to supply that value. With the aid of this one, you generate the same thing that we did in the R norm. R norm, instead of R norm, you're going to do this one in the R binom. See? But if you do this way, and the n equals 100 and size equals 1, that would give you that the percentage, the decimal, see? 67.33. You do again, see? 64.36, 65.35, 72.28, see? Different numbers. But those numbers are always around this number. See? See? By knowing this one, you're going to generate. You have to know that one number, probability and the size. See? Or you can do this in two ways. See? This is the same thing for that unloaded of air coin. We did that one. Okay. This one. And this is how that we generated the data. See? You can generate data like this. We have generated data in this particular sample. See, you go to the install package truncated normal. We're going to talk about the truncated normal. Because normally in practical application, we don't use the normal distribution. It's been truncated because that minimum value, you cannot remember the minimum value. If you start from the minimum value, it's enough. You don't have to worry about the everything that beyond that point. Okay. So here, before I go to that one, I want to come back here a little bit. This one goes this one 7. What is 150? I want to see something here. Okay. 8, 7 out of 150. The first number 7. Yeah. See. So let's say this one. Okay, this one. Okay. First day. Yeah, this should be like this. The first day. Okay. 9 defectives. Second day, 9. Third day, 6, 13, 1, and 7. On average per day, 7 out of 155%. Yeah, that's why I was curious earlier something wrong over here. So number of size of the trial for observation. See. So this one, separate this one from related to this example. Out of 150, how many will be defective? 9. Second day, 9. Third day, 6, 13, 1, 7. Here. Because of this percentage, it's not going to go that higher. Okay. Let's say that we put the 0.95 defective rate. See, almost everything defective. See, you can see clearly out of 150. Out of 150 should be set up like this way. See? So I'm gonna write, okay, this is 0.05, okay, 05. I'm gonna get this one and I'm gonna try something here. This one, 150. Okay, come on. 7, 0.05. Oops, no. Stop. Okay. Okay, so 150. This one, no, this is not the right page. 7, 150. 7, 150.05 equals 6. So 7 days. See, this is 0.05. See, this one, if you specifically give, see, okay, that's good. So I'm gonna get this one and set up like this way. Again, defective R binomial. I would say size. Size thinking size should be n. So if this way. No, then it's gonna go to n50. See? No. The size should be 150. It should be 7. Yeah. So size in number of number of times it's been done. See, that's how on average according to that setting that we have to set up like that way. So here it y number of access is right. The number of observation repetitions you want to see the size. Number of times y being observed. Yeah, number of times y being observed 7. Number of times y being observed. No, that's the problem over here. It should be n. This should be number of times y being observed 7. N equals 7. So number of observations, okay, this one size for n. This should n come first. Number of trials per observation. How many sample size? We would say number of trials per observation. Number of observation called size. Number of observations for the size. Like that. Should be like that. Yeah. See? So that's why size. First we put the n. And I get this one. So size n. Anywhere you can put n equals 7. Size equals 150.25. Just go with that one. N size probability. P. Okay. This one. Yeah, that's good. So I can depend and put anywhere that, but I have to make sure I specifically mention that one. Oh, okay, that's good. Oh, without putting anything. I'm not gonna put anything. 150. 7. And without that one, if you put like this, see, doesn't work. So make sure that n come first. You have to go with the sequence. N come first. If 7 size and this one, that works. So you go with their sequence. But if you're gonna name that one, you can switch the locations, but they are fixed sitting number of observations. And see how many times you're gonna observe, and many times. trials per observation called the size. See, size you have to give that one. See, then you can figure out, see, each day, see, each day how many defective? 8, 7, 8, 9, 6, 4, 7. And on average, how many like that? That's the one that I used. And this one we already did that one. And then this is that, as I said, that truncated normal distribution, we're going to use that one. If the aid of that one, I'm going to say mean. Mean would be, see, I'm going to generate mean, see. With the aid of that base SD and base this one, I'm going to generate means, see. I'm going to generate means. And then standard deviation, if you want standard deviation, do that one too. But you use the truncated this one. Install that one. Okay, it's already there. Okay. It's in use. Okay, that's okay. Why already see this one? Install package trunk node and library trunk node. This one, then you can find the head of this one. Means those are the mean. Minimum data minimum value is 18. See, I'm going to start from there. How many I'm going to generate per time? See, there's a for loop, double for loops. I'm going to generate a frame matrix. I'm going to set up a matrix. No, not available. See, number of rows. I'm going to show this one for 2 first. See, 2. See, number of rows. See, number of rows 2, 2, and the number of columns 2. And it's going to go from I goes from 1 to 2, J goes from this one, this one, this one. Okay. See, matrix being filled in. But the one that we had, okay, don't run because the computer it takes a while. If you computer very fast, you can run. I'm gonna say data 2. Okay, this one. I would say number of row means n row of what? That. How many rows? 100. Rather than call that 100, you can say that one. This one. N columns, number of columns of that. And that one. See? 1, 2, 1, 2, data frame 1, matrix 1. So there should be another one. Oh, that's right. Then for the loop, it's going to go from where to where? Not this one. N rows that. Okay. Not to 1 to 2. This one. This one. Okay. In column. See, data 2. And it is filling, see, one at a time. Go round. I'm going to round this one to certain decimal places, 1 decimal place. Okay, 1 decimal place. And keep going this one. And data 2, this one takes a while. Okay, I'm not going to run this one. For the minimum value is starting from there. You generate 1 at a time. See, starting from here all the way up to infinity. It doesn't go to infinity. If you want, you can set up the max as well. As a B, max 2 to truncate. They cut off. Okay, that means that instead of working with the whole thing, you can truncate. See, your normal distribution is like this. See, you're gonna truncate. See, from somewhere. See, from the minimum value, mean of data would be 80. See, the average would be 31 something. No, can you remember average? 31.44. Let's say average. See, center. See, but you are working with this one. See, you generate from there. You don't need anything beyond that one. If you want, you can cut off the maximum value. If you know the max, you can put the max as well. Cut off from both sides, left truncated and right truncated. This one, you can get the max. See? Max of data. You can remember max of data in the beginning. 1949. See, 49. 49. And for this one, mean gonna change from, see, from what? Column to column, see, column to column, mean gonna see from here. From here, I'm gonna pick mean one at a time from this guy. This, see, I generated means. Those means I'm gonna utilize here. If you want, you can do the same thing for standard deviation. But the standard deviation, you keep the same thing. So it's called the same standard deviation, good, rather than changing that one. But for the standard deviation, this standard deviation coming from here, okay? This guy's jth one, I will take into account. See, 1000 samples per 100%. So this one, J, how many? See, 1000. I have 1000 minimum. See, I need 1000. See, column. See, J means the column. See. So if you want left truncated, right truncated, 49 from this side. See? From this side, 49 from that one. That side you can truncate too if you want. See, this one 49. See, 49. So you work with, see, you work with this one. That's called the truncated normal distribution. See? That's the truncated normal distribution. This one you can say left truncated. This one right truncated. My convenience, I just did the left truncation only, and I generated 1 point at a time, and then I'm gonna fill in that matrix. I show that how the matrix is x1. See, keep filling. If you want, you can put the column number of rows. How many students? Let's say 5 students. But the 2 columns we're gonna fill in this one. Oh, sorry, I didn't change over here. 2, 5, and 2. You filling up. That's how they generated. Rather than observing, that's how we got our data set. X1, X2, like blah, 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 like that. All the way to 1000. If you do this one, that's how we're going to generate that. Okay. Okay. Then you get a rough idea that how what to do, and then let's look at this this one real quick, and then we can for that. This is for your only knowledge. Okay, these are for knowledge. This one, see, all these. See, this is one of this part you can use. You don't have to talk about all these. See, just one way of getting this done. You don't have to show all this. I'm showing you because my role is different than your one. My one is just to show you in a broader range that how things can be get it done. Okay, so make sure that one more time I'm gonna slide through this one slowly. You can see. Yeah. You just simply that focus on the question and then answer any way you want. There are so many methods that we discuss over here. All coming under the note. We note on the number 2 in the note. 3, 2. To 3. To 4. You don't need this one, just straight go to that, whatever that you want to do. These are all the notes, okay? Sorry, here, see, note, Q4 note, see, these are note, see. Yeah, this one, if you can see, end of note. Q5, Q6. So again, see. Q7, again, end of node. Yeah, it's within that one. Because of that, I just take this out. Here too. That one. Okay, this is end of node. Then this one end of node. Okay, this one fusion number 8, fusion number 9, parts ABC, ABC, 9 ABC, AB, number 10, extract query, nodes, 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 all these nodes, nodes, end of nodes. This one. Okay, then extract query node. This how we generate data like that. Okay, so let's real quick have this quiz on the midterm. Let's this is sorry, it should be midterm. This. Okay, let's see this one real quick. See this data set. Look at the below is a birth, weight, date, and gestational period collected as a part of the Child Health and Development Studies in 1961, 82, 62. Information about baby's parents, age, education, and whether the mother smoked is also recorded. See, mainly that. See, she's smoking or non-smoking. 1 and 0. See, 0, 1, 2, 2, 3. Actually, see, there are so many that categories. See, 0 never, 1 smoke never. Now 2 until current pregnancy, 3 once did, not now. So then when you go to see weight and the baby's weight being see then shown by this histogram, our histogram of the birth weight in ounces for the 50 newborns in this data set. If you wanted to explore, see, this is the code. Mother smoking might explain the variation in birth weight. What visualization might be helpful? See, you want to see that how mother smoking status is going to affect to the weight of the baby. So see, weight being explained by smoking status, weight being explained by smoking status, weight being explained by smoking status. Either see, box plot, scatter plot, histogram, everything. Faceted histogram, scatter plot, box plot, all the above will explain that the variation of that one D. Okay. If you want to explore the idea that mother's age might explain the variation in birth weight, how it's going to affect to that one, what would be the best way to see? Faceted histogram being given by the age. You have to be careful. Age is not a categorical variable. Age is not a categorical variable. Age is what? The continuous variable, continuous numerical variable. So because of that, you cannot even think of these faceted grids. This box plot, no. With respect to age, no, there's no such thing. Only thing this one, scatter plot. See, Quantitative to quantitative, quantitative, quantitative. See, this one quantitative, quantitative. No, there's no such thing. Quantitative, this one, there's no such thing. Only this one. Okay. So in this one, if you were to use the data to guess the mean weight of newborns in the population, what would be trying to estimate? If you go to the mean of that one, guess of the mean weight, you are trying to get some estimate of the mean weight of in the population, whole population, what we are trying to estimate. But to use this data to guess weight. Standard data, X, no, beta naught. Beta naught is what always? That's the weight, what? Weight with respect to what? If you were to use this data to guess, the weight is given. Weight has been explained with respect to what most of the time? The smoking status. Smoking status. See, even not that, yeah, smoking status. See, data naught. Data naught is related to what? Never. And then data 1, smoking. Data 2, until current pregnancy. Data 3, once did, not now, like that. Okay. So if you use this data to guess, okay, if we wanted to explore the idea, if we were to use the data to guess the mean weight of newborn in the population, we would be trying to estimate data naught. Okay, that's that data naught is nothing but related to what? In the empty model, even forget about that one with respect to this one. Think about that. You don't know whether which variable to be gonna utilize in order to explain that one. You can think about the empty model. Okay, you can think about the empty model. See, empty model. In the empty model, can you remember? You have the weight. See, you can get this one. See, no x here was no x was, but you have here what? Y is what? Weight. See, weight. Then you go to what? It's mean. Y bar is nothing but data naught. You can remember. See, data naught hat, which is B naught. Same thing. So who you can be try to estimate? The grand mean, the population grand mean, the population grand mean means population's average weight. So that should be data naught. Okay. And remember that we write this one. You can write this model. If you write this model in 2 ways, you can write the population version. Any data you can write, excuse me, data naught plus the epsilon. Here sample version. You can write y equals anybody's that birth weight, any baby's birth weight would be given by data naught plus error. See? Data naught plus error. See? Yeah, sure. Thank you. Yeah, I'm gonna keep recording this one. You can catch it up. Okay. Thank you very much. Have a good night. I finish it this one and then record. Okay. Thank you. Take care. Bye. Good night. Yeah, I'm gonna keep going on this one. Okay. And the output of favorite stat will see. Favorite stat is shown above. If they had a collected different sample of 100 newborns, what value would be different? See, this is for based on that one data sample. If you pick another data sample, maximum, minimum, medium, most likely all gonna change. Okay, all gonna change. So look at this one. Given this distribution of data, could the population of newborn weights be shaped? Given this distribution of data, could the population of newborn weights be shaped like a normal distribution? yes, since that sample, that the distribution is like this, you can get a rough idea. It is possible because the sample often do not look like exactly like the population that they were drawn from. They don't look like that population where that the data has been drawn from, but since it looks like that one, if you're gonna increase the sample size to make that one population, this all the gaps will be bridged, fill in. Okay, therefore it's this is okay. See, this is yes, okay, yes. Number 6, let's go to number 6. Assume this code has already been run, favorite stat. What will be the following line code do? See, R norm. You do this one, you're gonna see, you generate, no? You generate a random sample of one sample, okay? Generate a random sample of 100 data points from a normal distribution with the same center and spread at weight. Same center, same mean. See, R norm. See, wait. So see, why might it be helpful to calculate the means from a random sample? Random sample of 100 drawn from a normal distribution with the same mean and standard deviation as weight. Because the resulting sampling distribution give us an idea how much random sample mean could vary. See, sample means not based on one sample, based on so many samples. We get the mean based on so many samples. Okay, so many samples. See, so many samples. Because that will give you how that mean random sample means would vary from each other. So there should be 7. That's why we're gonna get the 100 sample. We're gonna get random sample of 100 drawn from means from the random samples of 100 sample of 100 samples. See? This is not 100 sample. This here sample of 100 data point. But here we say that yes, when we have to calculate the mean from a random sample, means from random samples of 100. See, random samples. They don't say how many, but the sample, each random sample has a size 100. Drawn from that one gonna form, because we're gonna pick this random sample of size 100. Why we have to pick so many random samples? Because that will give you an idea how that sample means could vary. Okay, 7. Okay. The sampling distribution of means above was created with this code, sampling distribution. See, SPOM, this one, and the histogram. And remember, this has been done this way. If you were to stack up all the bars, what would be the total? What would the total be? Sorry. What would the total be? If you stack up all these bars, that's the what? That's nothing but what? How many sample means? How many sample means we have? This is one sample. See, you get 100 people, their average, you get them average. How many averages? 10,000. 10,000 averages. 10,000. If you keep adding these frequencies, that frequency will add to the 10,000. If you stack up all these bars on top of each other, that will give you the sum of frequency will be nothing but, see, total number of observation, total number of sample means, see, total number of sample means. See. That's what we're talking about. If we go over here, see, from the 8, just see that you have sample distribution y bar here, like this one. When you have a frequency, see, if if you stack up, see, this one on this one, and these heights, this height, we don't know. But that's called the sum of all frequencies. Sum of all frequencies, sum of f is nothing but total number of y bars, which is 10,000. 10,000. 10,000. The answer is B. So number 3, we should go back to number 3. And then go back to number 3. Number 3, so is the answer again. Number 3, what we are trying to estimate. Okay. Number 3, what we are trying to estimate. Beta naught. Beta naught is nothing but mu plus epsilon. Okay. This one y bar plus e. See, beta naught is mu, the one that you are trying to estimate. So answer is again B. Okay, 8, 10,000. Okay. 10,000, 8, 9. Let's go to 9. Which of the following is a true statement? See, you generate the sampling name of the creator with the aid of this code. What is standard error of this distribution is smaller than the standard deviation of the that weights with the single one. Standard deviation of the sampling distribution is a small. See, that's true. Standard error. Standard error of this distribution is smaller than the standard deviation of that one. Standard error. Number 9. Standard error. Okay. So number 9 is standard error of the sampling distribution of y bar, which is sigma y by sigma over square root n. Okay. Square root n always less than what? Samples go to that standard deviation of weights. Okay. Standard deviation of weights. Standard error means standard deviation. Okay. Standard deviation. Standard error means standard deviation of the sampling distribution of y bar. Standard error. Standard error means standard deviation. Same thing. The sampling distribution means sigma y bar, which is sigma over square root n, is less than the standard deviation of weight, which is given by W stats. Weight dot stats, go to that one, dollar sign and see. So the answer should be A. Okay. The answer should be A. It should be A. Go to 9, 10. Again, the sampling distribution again built up like this way. Someone tells you that their baby was 116 ounces at birth, only baby, one baby, okay? What is the likelihood of a baby having a birth weight of 116 or lower in the population? No, we cannot do like that. We need the sample mean. We need a sample, not only one baby. We need a babies, certain number of babies that average, if you know, then we can find it. Therefore, I'm not sure because I cannot tell the likelihood of a single baby having such birth weight from this sampling distribution. No. Sampling distribution is for several babies. So D. Okay. D. Look at the variable. So variable smoke should be factor, but we created a model using smoke to explain variation weight and call smoke.model before we turn it into a vector. The output of smoke model is shown above. What is wrong with this approach? We can talk about the number 7. Weight versus smoke. Smoke. See, before turn it into a factor. If it has not been taken into a factor, the computer, the machine, the robot gonna think those numbers. See, okay, smoke numbers. Look at the numbers. They were not factorized. They were not factorized. They're gonna think these are numbers and then try to consider this one as like a quantitative variable if it's not being converted into a factor or like a categorized. Okay, you can remember we had that discussion. They still think these are quantitative, and then they're gonna do the regular regression, not the group regression. They try to do the regression, something that should not be, not happen. See, that will give you this kind of. So okay. What's wrong with that one? The wrong is that the machine gonna think those numbers are numeric and then do the regular regression. We made the variable smoke into a factor and save it as smoke.factor. Then we fit a model that use smoke factor to explain variation in weight. All the R code for this is shown below. See, factor. See, you have a factor. Go to the gestation dot 100 at smoke levels 0 to 3 levels. I'm gonna put the new one. Never smoke now until current frequency once did not now. Close it. And then smoke factor, you're going to convert this into a model. Which GLM equation specifies the smoke factor model? How many levels you have? 1, 2, 3, 4. Okay, 4 levels. If you have a 4 levels, you need only 3. 3 indicator variables. 3 indicator variables. See, 3 indicator variables. If you have this one, you need. Okay, I'm going to get this one out of this one a little bit. Okay. Look at this one. You have a see number 12. See, you have see, you can write y equals c v naught plus b1 x1 plus b2 x2 plus b3 x3 plus error. It's gonna be what? It's gonna be you can say never. This one for what? Smokes now. Smokes now, then x1 equals 1. x1 equals 0, otherwise, okay? Otherwise, I'm going to put OW, otherwise. See, this one never. See, if you want, you can see that one never, okay? This one, x2. x2 is those are what? x1, x2, x3 are dummy or indicator variables, okay? Indicator variables. So second one, we can say smokes now until current pregnancy. So x2 equals 1, x2 equals 0, otherwise. Okay? Otherwise. x3. x3 will be one speed, not now. So x3 equals 1, x3 equals 0, otherwise. So the answer should be A. You need 3 indicator variable to tackle the 4 levels, 1 less than the number. Okay. Look at next one. See, they run that one. See, you get the values for see B0, B1, B2. Smoke factor, sorry, B0, B1, B2, B3. Sorry, B0, B1, B2, B3. We made the variable smoke into factor and save it as a smoke factor. Then we fit a model that use smoke factor to explain variation in weight. The best fitting estimates for the model from the LM function are shown above. What would be the model's prediction for the weight of a baby born to a mother who smoked until the current pregnancy? Or until the current pregnancy. So this one, if you go to this one, see. So you know this one, see. This one is X. X means smoke. Okay. Categorical. This one you have what? Y, weight, quantitative. Okay. You have a levels. I would say N for never. Smokes now, SN. Until current pregnancy, UCP. And the last one, once did, not now. So first one, I would say never. Second one, smokes now. Third one, until current pregnancy. Fourth one, once did, not now. So Y bar N B naught, B naught. Then Y bar Sn, the gap between that one is V1. And this one, let's say I'm gonna make it this one maybe below or above, okay? Not necessarily this one, Y bar until current pregnancy. So the gap, this one is B2. Then let's say Y bar once did, not now. And that gap B3. See, look. Y bar 1, 2, 3. See? So they were given us all the values. So this one, we need that one for somebody who's in the second category. What would the model prediction weight of baby born who smoke until the current pregnancy? Until the current pregnancy. See, B0 plus B2, B0 plus B2, B0 plus B2. For this one, B0 plus B2. B0 is how much? B0 plus B2. B0 is 122.159 plus B1, B0, B1, B2. B2 is 3.84. 814. So the answer should be anybody's that average, not prediction. Prediction should be, answer should be B. For this one, answer should be B, 12, B, 13, I'm sorry, 13, B. Okay. So then ANOVA table, if you get the ANOVA table, we make the variables smoke in the blah, 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 ANOVA table. For this one, why is the degrees of freedom for the model 3? Why is the degrees of freedom for the model 3? Model 3. So freedom for the models, okay? Why this model is 3? 3 is what? Because there are 3 parts? No, because there are 3 additional parameters estimated in the factor model compared to the empty model. That's true. See, 3 extra one. 1, 2, 3. in addition to this one. This from the empty model. These are the additional parameters. Additional parameters. Additional parameters. Because there are three additional parameters. Three additional parameters estimated in the small factor model compared to the empty model. That's why it's 3. Okay. B. Then go to the next one. Perhaps the mother's age could explain some of the variation in birth weight above the depicted out in this model, age model. See, which equation represents this model the best? See, this B naught is B1. See, y equals B naught plus B1 times X. B times, see, B naught plus B naught. This is the age. This is the weight. This is the age. See, baby's weight, mother's age. This is B naught. B1. So answer should be okay. Perhaps the mother's age. Okay. What does that 0.43 mean? 43 means, you know, that's the increment. It's the increment to add on to the prediction of weight for every year of mother's age. Increment to add on to the prediction of weight for every year of the mother's age. You know, that's the slope. Okay. So let's go to the next one. Okay. Okay, you're going to compare to empty model and then, you're going to compare weight with the age, weight with the smoke factor, same Y, okay, same Y. They say the above have included the ANOVA table for 2 models, weight, age plus other stuff, weight, smoke factor, others. Why do these 2 models have the same value for SS total? SS total, why? Because SS totals are based on the residuals. See, 25. See, this one, SS total. Based on the residual from the empty model. That's true. Because the SS totals are based on the same outcome variable. That's true. Why? Because they are based on the value from the same data set. That's true. Same data set, same outcome, empty model. See, all the above reasons. So this one again, see, above we have included. Why does the model with the small factor have a larger pre? Larger pre. This one, small one has a larger pre. Because the larger pre, larger F. See, larger pre, larger F. This one, see, smaller, smaller. See, the reason is what that more being explained. See, more error being explained by variation being explained by this model. Okay, small factor model. So you can reason in that one. Okay, 18. That's 18. 19. Above we include the ANOVA table for factor. Which distance is the basis of the SS error? SS error, sum of squared error, being measured from where to where? Distance between the data point and the model prediction. You know that. Y minus Y hat is the data point. Y is the Y hat. B. Then 20. This one. Smoke and age one. Your classmate take a look at these results and suggest that you judge these models using F instead of P. Why is this good advice? Yes, instead of P, see, you can go to the F. Because F takes into account the degrees of freedom, see, takes the degrees of freedom in account, see. And the smoke factor model might just have a big P because that model used more degrees of freedom. See? More degrees of freedom. See? See? More degrees of freedom give you, see. See? So instead of comparing the pre, better to compare This one, because the more the degrees of freedom has been taken into account. A. Okay, let's keep going. Then this one, see how that this data set, see, in this quiz we will focus only on the ratings that females gave to the males and only, oh, sorry, this is a speed dating, is a data frame with the 276 observation and 22 variable data come from a study of speed dating in which each participant participated in a 4-minute date with a member of the opposite sex. At the end of the day, they each rated the other on various attributes. In this quiz, we will focus only on the ratings that females gave to the males and only on a few of the variables. Thus, the variables below, except for the two variables that indicate the race of each participant, are all females rating of their male date, each on a 10-point scale. Like F, attractive F, intelligent F, fun F, sincere F, shared interest F, partner ESF, race F, okay, and race F like that, okay. So this one, I think that I have to go to the other class. These ones that you can try, okay. Then if you have any question, just email me that. I think these are not hard because you don't have that many questions, only 12 questions. You can easily figure this out. Okay. If anything is not clear, just let me know. Okay. Because I have to jump into the other class. Okay. So you guys have a good night. Stay safe, be well, and then see you guys on Monday. Okay. Take care. Have a good night. Thank you. Bye bye.